Okay, assalamualaikum and good morning. So, welcome back. I think before we start, so let me remind you about tomorrow's test. Okay, I hope everyone agrees to that. So, I think there's only one person left who has not agreed. If you can actually inform him to agree, then no, whatever it is, majority is already agreed to the test tomorrow. Okay, so I just need to confirm with that one person. Right. So today we'll continue with what we have lectured before. Still from lecture 9. So I believe we have gone through all the idea of proper time and four velocities and 4 acceleration. And essentially we have defined what is 4 velocity before this. So essentially we have this called oh, my tab is not working. On a minute. So essentially what we have defined is to have your position vector differentiated with respect to the proper time, and the components are given by this. Okay, so essentially the spatial components correspond to the ordinary velocity, but essentially it's modified by the relativistic factor, which is the 1 on square root 1 minus v squared on c squared. So that's dependent on the frame velocity. So you will have that factor coming in, multiplying the ordinary velocity. And then the fourth component is just your speed of light multiplied by the same factor. And the same thing we have actually defined your 4 acceleration by differentiating again the 4 velocity with respect to the proper time. The components are a bit complicated, slightly complicated than before, because we have the possibility of your relativistic factor to depend on your time coordinate over here. So you have this part multiplying v, and then you have your ordinary acceleration multiplied by gamma. Okay, and your fourth component also will be depending whether your gamma is essentially time dependent or not. Remember, gamma is essentially this. So in other words, if this is this frame velocity is just constant, then there will be it will be 0 here. But as I said in the previous lecture, sometimes we want to consider the frame that is attached to a particular particle that's moving. So that particle might have its own frame, okay, the proper frame, but according to the observer outside the that proper frame, we will see that the velocity is actually changing, okay, and in other words, that can be actually dependent on time. So that's why we have that particular factor coming in. Okay. So I think we've gone through this. So in the proper frame, then you can actually just have the ordinary velocity. Oh, the other thing is one should highlight the fact that your v mu here is essentially what we call time light. Okay. and then the other part is essentially your A mu is going to be space line. Okay? So normally if it's space line in one frame, it will continue to be space line in other frames. Okay? So the one that we have actually shown is in the case of the proper frame, then you can actually see that this is going to be space line. So that means if you take a different frame, then it will be also space line. And then finally, we actually show that the contraction of your velocity, forward velocity with a forward acceleration will always give you 0. That means orthogonal in terms of space and time. Okay, and this is actually a general feature of what you call time-like vector, time-like forward vector being orthogonal to space-like forward. Okay, so perhaps that particular fact maybe will be given in the assignment how to prove it. So the next thing that we want to do is if you have two four velocities, so here is one of them is u mu, and then we have another v mu, and then we have your spatial components given by the vector u, small u, and the spatial components here given by the vector small v, and then you have the fourth component. Okay, we just write it as u4 and v4, and one would like to see what is the meaning of a contraction between this forward velocity with this forward velocity. Okay, so a good thing to look at is that you can more or less sort of fix one over forward velocity to a special frame. In this case, you can consider the rest frame, or if you want the proper frame for one of the particle, and then you can actually see how the other particles moving relative to that the first particle. So if you do that, so that means your u mu here will take this particular form. Okay, so you have zero velocity here, and then your fourth component is going to be just c. Okay, and then what about the other one? Well, we still have this thing, but now you remember that in the fourth component, essentially, if you remember, your v mu component is gamma, gamma depending on the frame, of course, and then your spatial components, okay, and then this is going to be c over here. So in other words, v4 will be gamma c. Okay, so we have that, and then for the spatial part, you have your ordinary scalar product between the two vectors u and v here, but u has been set to be equal to 0, so that gives you 0 here. This is 0 vector. So you're left with v4, which is given by gamma c, and u4 is essentially in this particular case will be just c. Okay, so you essentially what you have is you get minus c squared times gamma. And what is this gamma? Gamma is the relativistic factor according to the relative velocity. So meaning how this particle, for example, that has this what I call fixed to the rest frame, c is the other particle moving with respect to his spring. Okay, so essentially we have that to be the answer for the case of contraction between two four velocities. Okay, and to understand this properly, you might want to consider, for example, how the four velocity of v mu with respect to this four velocity of this sort of reference particle in this way. So this four velocity of v mu will have components which are going to be, so you can always you remember just ordinary vector decomposition. Given a particular vector u and v, say this is in 3 dimensions, you can always decompose your v in terms of 2 parts, which is the one which is parallel to u, which is given by v dot u, okay, and then the other one would be the orthogonal part. Okay, so this will be the orthogonal part. So okay, I'm just going to put it as orthogonal part, and then this will be something in the direction of orthogonal to u. Okay. So you can have this kind of decomposition. So in the same way, you can write now v mu, this v mu, as follows, where you have a component which is parallel to the four velocity of u, and then there will be another component which is going to be orthogonal to the component of u. Okay, so but as you can see that earlier we have already fixed u mu to be equals to 0c. So the one that can be orthogonal will be something like this. Okay, so you can actually see that u mu, u tilde mu is going to be equal to 0. So that means I would need to have a 0 here, so that when it multiplies this c, gives it 0, and then of course this one I can have essentially any non-zero component here. Okay, so then essentially that will actually satisfy this u tilde mu is orthogonal to u mu. Okay, so essentially this is what it is, and you have the relativistic factor here, which is given by the relative velocity here. Okay, and this is given by this u tilde mu. Okay, so that gives the u tilde squared. Okay, right, and then so this is the thing that we mentioned just now. So essentially what's happening here, then you can actually substitute the form of the v mu that we had here into, let me go up, into the form that we have over here. Okay, so essentially that gives us what I call, well, actually you're using this one. Okay, so essentially you have the u mu, and then your u mu contracted with u tilde mu will be equal to 0. So in other words, over here you're going to get your minus c squared from u mu is 0c, oops, so dot product is 0c. This is your inner product. Okay. So and then essentially what it does is it simply project the velocity along the direction of your u mu. Okay, So that is a kind of physical interpretation of this quantity here. Okay, so the part which is orthogonal to u mu is going to it's going to drop off. Okay, so the ones that left what you call in this contraction here, your inner product between u and v will be just a component parallel to u, which is essentially a generalization of what you know for u dot v in the three-dimensional sense, because this will actually essentially give you a projection. Okay, a projection. For example, I can think of v being projected to the direction of v. Okay. So, you remember we have that in our three-dimensional case. So the part which is orthogonal is going to drop off. So you only have the ones which is parallel to it. Okay. So let's consider now an example. So here is a world line given to you in terms of proper time for a particular particle. So this particle is essentially accelerating. So it's given in terms of this curve, and you can actually recognize that this curve will give you a hyperbola. Okay, so and for simplicity, we have actually set this to be 0 for y and z, so it's just moving along x direction. Okay, so if you look at what this world line is going to be, okay, it's going to be this particular hyperbola. Okay, so remember how you can actually do this. You can actually take x mu tau, okay, as a function here with x mu tau. Okay, so in other words, you're going to get a contraction of, well, you multiply you get this squared minus this squared. Okay, and essentially your cos and sine, or hyperbolic cos and hyperbolic sine, will have to obey this. Okay, and essentially that will give you this particular hyperbola equation. Okay. So from there you can also get your time coordinate in this particular case. You're just rearranging this hyperbola equation to be written in terms of the spatial coordinates, okay, in this form. Okay, and the world line is curved, so that shows there's a presence of acceleration. In fact, you can actually calculate what it is in the following notes here. So for example, the fall velocity, you are already given the components here in terms of a function of tau. Okay, so all one needs to do is just to differentiate with respect to tau. So you differentiate this part, which is the motion along x. Your y and z essentially is not given as a function of tau, so that's 0 here. And then your time component, okay, your hyperbolic sine. So when you differentiate, of course, you get your cos turns into a sine, and your sine turns into a cos. Okay, and then you can check again. So this will be now the fall velocity. So you can check u mu now should give you minus c squared. Okay, and that's what it is. When you just contract this, you have this square minus this square, and that gives you a minus c squared. Okay, and your three-dimensional velocity is given by this. Okay, so you can essentially replace this by the in terms of your time coordinate if you want, but then you can use your chain rule, and then you actually know what this is. Okay, u1 is coming from the one before your shine, and then u4 is coming from your quotient. So essentially what you have is you have c hyperbolic tangent times sorry, not times, function of a tau over c. Okay, and hyperbolic tangent is going to be less than 1 because you remember what is hyperbolic tangent is given by e to power x minus e to power minus x over ex plus e minus x. So this is bigger than this one. Okay, so that gives you a quantity which is less than 1. So in other words, your three-dimensional velocity is going to be less than c. Okay. And then we can continue to calculate the forward acceleration for the given world line. So it's just the derivative of the forward velocity with respect to the proper time. Again, you can do the differentiation, so it gives you that. And if you take the contraction of a mu with a mu here, then it gives you something which is going to be positive because you know that it's going to be spaceline. Okay. So you can actually see that the a that comes into this particular called magnitude of your forward acceleration is actually coming from the factor which is the earlier factor that we introduced inside your hyperbolic function. Okay. Right. So that's an example. I think that's it for this particular lecture. So let me just prompt over here. Are there any questions with respect to this particular lecture? I guess no. Again, let me try to remind you, I need the confirmation of another student, so I already WhatsApp the name of the student. Okay, so please reply about tomorrow's test. Okay. The other thing about tomorrow's test, make sure that you have your notes and your assignment solutions because it will depend on those. Okay. So let me continue. If there's no questions, let me continue with the okay. So essentially what we did in the last one, in lecture 9, we are doing kinematics. So you just define what is your forward velocity and your forward acceleration, and of course your position forward vector. So that will actually all the things that you describe it at the what we call the kinematical variables. So now the next thing that we want to do is to introduce dynamics. Okay. So one has to somehow be able to talk about equations of motion. So usually when we talk about equations of motion in classical mechanics, then you really need to introduce Newton's law, for example. We will have some kind of analog of this Newton's law inside special relativity. Okay, so let us recall a few things. So your equations of motion are given by F equals to ma, or more what you call a much more general way of describing F is essentially in terms of the momenta, because if you use ma, you probably have realized this, much more basic course, you are essentially what you call assuming that your mass doesn't change with time. But with P, you can allow your mass to change with time as well as your velocity change with time. So this is a much more general way of describing your force. So it's a rate of change of momentum. Okay. So in the context of Newtonian mechanics, once you have this equation to be obeyed, then we know that it's going to be an inertial frame. Okay. So in the case of what you call special relativity, we have not really defined properly in terms of force, okay, but we know that the inertial frame in both special relativity and classical mechanics are the ones that says a free particle will just continue in a straight line. Okay, so that's the one of the common things for inertial frames. Okay, so you essentially have that. Okay, and if for the case of a particle which are interacting, for example, then you consider the total force to be zero, then you can actually say that, okay, we have conservation of linear momentum. So these are some basic things that we have seen. Okay. So what we're going to do next is how to generalize this particular idea. Okay. So one of the things that you want this to be valid is in the case where when you have the total net force equals zero, okay, then you still have conservation of linear momenta. Okay, and we want it to be true in all possible inertial frames, including the one where you have the limit where your inertial frame is going to go as the velocity going to zero. Okay, so in particular, if you think of the proper frame of particular particle, then this fact is still in general is true. Okay, so that is the thing that we wanted to do. So the only thing now is to allow the possibility that your mass will be changing. Okay, just as I said before, why is this a much more better way to describe your Newtonian force is because you can allow your mass to change inside your momenta here. Okay. So our starting point would be to essentially write a similar equation as the one in Newtonian mechanics. So in Newtonian mechanics we have that, okay, m times v, but now what we're going to do is to make an extra what you call extra feature of it. So let me rewrite this thing. So the extra feature now is to be able to make your mass to be changing. So in this case, we need something to some variable to be able to change. So we say that this is possibility of your mass depending on the velocity. Okay? And we'll see this later on. Okay. So in other words, we have the mass as a function of velocity. In other words, this can actually change with the velocities. Okay. So when you take the velocity in the limit of v tends to 0, your mv will go to m naught, which is what we call the rest mass. Okay. So go down, let me see. Okay. Okay, we go to that example. So the assumption now is what's the other thing that we want to assume is the fact that you have conservation of three momenta when there's no net force. Okay, so somehow or other we would like that to continue in the special relativity. So in other words, if you allow the mass to also change with velocity, so your velocity dependent mass times the velocity, okay, the total sum, meaning you look at the total momentum, it should be conserved and that should be a constant. Okay, so now we need to investigate a little bit what is this function. Okay, and in order to do so we need to go to a case by construction and hopefully constructed well enough to actually give you what function this mass going to be. Okay, so let's consider two particles of rest mass m naught. So in other words, we have some particle of the same mass or same type. Okay, and the particle 1 has velocity minus u. Okay, so this would be this way. So I should mention that it's traveling in the z direction here. Okay, so here is the z-axis. Okay, to the frame, say k here, or frame k, and that particle is actually moving in the negative sense along the z direction. Okay, and then you have another particle, particle 2. It will have again moving inside this particular frame of k dash, okay, moving along the z direction with a positive sign. Okay, so it will be plus u in the z dash direction. Okay, so this is the other frame, and we would like to allow these two masses to collide. Okay, and then after the collision it will coalesce or combine together to form a single particle with mass capital N. Okay, so that's essentially our setup. Okay, so let me go to the next page. So in the K frame, okay, so let's do the four velocity now. In the K frame, you see that okay, your velocity, the spatial components of your velocity is given by uz equals to minus u, ux equals 0, and also uy equals 0. In this case, we don't consider really y because everything is in the here it should be the xz plane. So you have that, okay, and your u here has velocity, what you call magnitude square, as simply u squared, okay, and we denote this as u1. The 1 here is saying that this is particle 1, and then m2 inside the frame of k, then you need to use what we call addition of velocities. So you have ux equals to the frame velocity plus the particle velocity, but the particle velocity in k is 0, so you get v plus 0 there, and then you have 1 plus v uv on c squared. If we look back at the relative velocity, the addition of velocity formula earlier, then you have this formula, and that gives you equals to v, just the frame velocity, So now the second particle will actually being seen, sorry, uh, to move with velocity along x direction because it's inside this particular frame which is moving. Okay, and then your uz, okay, then your uz will be having this what you call magnitude u, okay, from this picture here, divided by gamma v. Okay, remember in this particular case, what happens is that there is no your particle is actually moving orthogonal to the what you call the frame, the direction of the frame propagation. Okay, so essentially that only gives you equals to that. So in other words, the magnitude of your u squared for the second particle is given by this. So this is u2 squared, second particle. So now what is the assumption that we want to have if you have conservation of momenta? So in other words, there will be a conservation of the z component of the momenta. So the first particle, the z momenta would be just the mass times minus u. Okay, so you get that. And then for the second particle, essentially you get the mass times, here, the mass times uz, which is actually equals to u on gamma v. Okay. So in this particular case, then you can start to rearrange this. So this is by conservation law here. So then you'll be able to express your m2 in terms of m1 and the relativistic factor according to this relative velocity of the frame. Okay. So our requirement here is that when u goes to 0, your mass will go to the rest mass. Okay. But in the case of m2, okay, m2 is given by that. Okay. And your u2 magnitude is given by this addition of squares. So you would actually see the following function here. So this is m of u2. Okay, remember this is not multiplication, this is as a function. Okay, so when in the limit of u goes to 0, this part will disappear and you are left with this v squared, or we can rewrite this as m as a function of v. So now this second particle will have a velocity dependent coming from the velocity of the frame. Okay. So from there, one substitute back into here. Okay, in this particular limit u goes to 0, then I will have m2 over here equals to mv. Okay, and then your m1 goes to m0, the rest mass, okay, times gamma v. So this would be the formula for the what you call relativistic mass. Now, how are we sure that this actually works? Okay, we can essentially substitute back to the equation that we had earlier. Which equation is that? Oh yeah, sorry, equation star. Okay. So then we can plug in what your M1 is and what 2 is. Okay. So M1 is given by this mass dependent on U1. Okay. And M2 is dependent on U2. Remember that U1 and U2, U1 is the magnitude of velocity of particle 1, and U2 is the magnitude of velocity of particle 2. Okay, so if this formula is consistent, then it should obey this particular equation. Okay, but you can actually see now that okay, this equation has a common factor of u, so I can remove this, divide it by u, and then essentially what I want is to consider just minus m1 plus m2 over gamma v. Okay, I'm just what you call factoring out the common factor of u then. So let's see whether this actually works. So mu1 is given by mu, okay, over here, okay, and then mu2 is given by, where is it? Yeah, here. So this is the magnitude of, well, this is magnitude squared of u2. Okay. So essentially we have that mu as a function of u, and then m as a function of this complicated thing, which is actually your u2. Okay. And remember that this is going to be divided by gamma v. Okay. Gamma v here, did I explain just now? Gamma v is just a relativistic factor coming from the velocity of the frame. So this we write as gamma v. So now this is going to be looking a little bit complicated here. So I would need to have m as a function of u given by this formula. So I'm going to replace this v by u. Okay. So I have the m naught times gamma u, and gamma u is 1 over square root 1 minus u squared or c squared. And for this one, again, this is looks a little bit complicated, but no, bear with me. Gamma v at the denominator will bring up the square root factor. Remember that gamma v is this. Okay, so 1 on gamma v will bring that square root factor on top. So that gives you that. Okay, this is your 1 on gamma v, and then your m as a function of that. See, so this would actually appear inside your gamma factor, you know, because your gamma factor now depend on this velocity or this speed. Okay, so I'm replacing your u2 by this square root. So what do I need in this gamma is this gamma is gamma u2, and it's going to give you 1 minus u2 squared on c squared. Okay, but u2 squared is given by what? This one. Okay, and essentially that gives you this factor underneath. Okay, so okay, looks horrible enough. Okay, one of the things that we can actually rewrite this thing over here. So let's take this part. Okay, and I will let you do the algebra to confirm this. This is true. You can actually write this square root underneath as 1 minus v squared on c squared, and then 1 over gamma v squared. Okay, that will give you minus 1 minus v squared on c squared. Remember, this is at the denominator, and then you have u squared on c squared. Okay, so that is the whole thing. Okay, and then you can see that, okay, I'm going to have a factor of 1 minus v squared on c squared on this part, and then another factor of 1 minus v squared on c squared on this part. So I can pull out that common factor outside the square root, and it becomes 1 minus v squared on c squared times square root 1 minus u squared on c squared. Okay, and that gives you this particular thing. Okay, I hope that you have to verify yourself to convince it. Okay, so in other words, now we have remember, this is coming from your gamma v, and then I have another 1 minus v squared on c squared coming from pulling out this factor from there. Okay, so I have that, so this gives you 1, and then I have m naught over square root 1 minus u squared on c squared from the second term, added with this minus m naught 1 times 1 over square root 1 minus u squared on c squared. So that essentially cancels off. Okay, and that's equals 0, which is what we required from the conservation of the z component. So in other words, that formula works. So now we can start to use it with confidence. Okay, and we can now define your three momenta as a function of the velocity u given by this. Okay, so this will be the velocity dependent mass times the velocity itself. Okay, and this would, no, if you use this, the formula above, then this is actually equals to m naught, your rest mass, divided by 1 square root 1 minus u squared on c squared multiplied by u. So this is the right three momenta that should be conserved in this particular picture. Okay, and this is good because it will be compatible with the formula that we have not to say predict, but no, we have essentially posited it in some sense, because you want it to be parallel to your v mu, your 4 velocity. Your 4 momenta now is actually something which is proportional to the 4 velocity by some constant which is not dependent on the frame, which is now given by the rest mass. Okay, so essentially this works out, and then you can actually see that the spatial part will actually correspond to that. Okay, so this is your gamma v times v times m naught. Okay, so that gives you the three momenta, and then the 4 momenta falls in by using the 4, what you call the fourth component of the 4 velocity. Okay, you get that. So essentially, previously we do not really know what will actually correspond to the 4th component of p mu, but now it becomes if we use this particular posited formula earlier, then this is actually correspond to your 4th component of your 4 velocity. I hope this is not, it seems to be a bit contrived, but no, everything should work out in the end. Okay, So finally, your components are just given by your velocity dependent mass times v, and then velocity dependent mass times c. Okay. Okay. Let me see. Okay. So finally, if we have the three-dimensional momenta to be conserved, then what's going to happen is that your four momenta is also going to be conserved. Okay? So now, in other words, you have conservation of the three momenta, that would imply your conservation of four momenta. Okay? So let me write that. Conservation of three momenta in the relativistic sense, okay, implies conservation of four momenta. Okay, so that is the conclusion of this part. One just to give you the gist, we do not have initially how a way of defining your mass which would actually change with respect to the velocity. And then we construct it by some example and then assume that you have conservation of your three momenta, and then you get a formula for the relativistic mass. Okay, and then finally we get to the point of the conservation of your four momenta with the fourth component coming in. And we'll see later on what this fourth component of your four momenta. Okay, and I don't think I have time to continue now. If I start this new thing, then I will not be able to finish it in this 5 minutes that I have. Okay, so I will stop there at this stage. So let me go back to you. Let me download the attendance. Okay, that's done. So I would end the lecture now. Is there any questions before we go? The test, let me tell you about the test tomorrow so that you can actually prepare yourself. As I said, bring your notes and your assignment solutions, and the question will be dependent on that. And there will be two sections. Okay, and there will be section A and section B. Section A are essentially questions with short answers. Okay, and then section B, there will be a long question. I'm giving you two questions, but you only have to answer one. So there's a choice for the section B. Section A, you have to answer every question. Any question about the lecture or the test tomorrow? Everyone's happy? Are you there? Okay, please tell the person, because I have my, no, the one in SMP, there's one more person that didn't respond to the question I asked to agree on the tomorrow's test. So please inform him. I'm not sure whether he's in the list or not in the WhatsApp list. Okay, so if he's not informed, then please inform him about the test tomorrow. Okay. Okay, that's good. Okay. Okay, then so be there slightly before 9 tomorrow, because we're going to use the lecture time slightly before 9, and then I will start off by telling you, the boring rules of exams, and then I will stay there for about 5 minutes just to see if there are any questions from the students about the test questions. Okay, so be there slightly before 9. Okay. Okay, everyone. Thank you very much.